Hello, and welcome to this episode of Madison's Chemistry. Today we're going to be discussing rate orders. So the two goals I have of this video is to 1. Distinguish between first, 0, and second order reactions, and 2nd, to be able to use experimental data to be able to solve for rate orders, which is going to be very similar to something you'll have to be able to do on the exam. So first, I figured it would be helpful to make sure that we define what the rate order of the reaction actually means for each of these, so that when we're solving for the rate orders in part 2, we actually know what these values mean. Okay, so if we have a 0 order reaction, that means change in concentration does not affect the rate. So let's say we have molecule A going to molecule B. And this is just a very simple reaction. So say we increase concentration A to B to A. It was originally just A, and say that this rate here, so this is first, second. And so the first one, we get a rate of 1 molarity per second. Remember, rate should always be in terms of molarity per second. Okay, so then second, when we double this, we might expect the concentration or the rate to also double, but zero order reactions are pretty wonky. So what we end up just getting is that the rate is still 1 molarity per second, and that this does not change. Okay, so now let's go over first order reaction. Okay, so this means that change in concentration is directly proportional to rate. So if we take concentration of A and goes to B, this is our first example, and our rate is 1 molarity per second, and let's say we increase the concentration of A by a factor of 2, that means our rate is going to be doubled. So we'll get 2 molarity per second. And then let me move this example here down a bit. Okay. So let's now say for second order, so change in concentration is going to be n squared, the rate. So let's go over what exactly that means. So let's say our original concentration, we just have A going to B, and our rate is 1 molarity per second. Well, let's say that we double our concentration of A, then our rate is going to be 2 squared, which is going to be 4 molarity per second. Sorry. And then third, we can triple our concentration of A, and that means our rate is going to be 3 squared, which is 9 molarity per second. Okay? So now if we're actually trying to do a problem, we can remember that the rate is going to be K times the concentration of A raised to some power, B raised to some power, M, and C raised to some power L, we can say. And remember that these are actually all just the reaction orders. And they must be determined experimentally. So, looking at this question here, it might be easy to say, oh, I think that the rate is just going to be K times A cubed times B to the 4th times C squared. But this wouldn't make any sense, right? So that would be saying that this is a third order reaction. this is a fourth order reaction, and this is a second order reaction. And I mean, we talked about second order, that's definitely possible. It means it's going to be squaring that. But a fourth order and a third order reaction are very unlikely. And also, what we have to do is we have to sum up the entire reaction order to determine the overall reaction. So that would be summing up these exponents. It'd be 3 plus 4 plus 2. That would be the overall would be 9. So we know that doesn't make any sense, right? So yeah, unfortunately we can't just look at these exponents to determine the rate order. So what we have to do is we have to look at the experimental data. So that's what we're going to be doing here. So if I were to set up to solve this problem, what I would want to do first is just look and see, okay, let's look at experiments 1 and 2 only. What's the one thing that's changing? Well, here, for concentrations A, there's no change, and for C, there's no change. So we're going to be looking at B. So that means I can go ahead and set up my expression to say 0.7 divided by 0.35 for 1 and 2. Let's make that clear. Equals, to the power of n, equals the bottom one, because we want to keep it consistent, divided by 8 times 10 to the negative fourth. So we can see easily that 0.7 divided by 0.35 is going to be 2. So we get 2 to the n equals this value here. And if we plug it into our calculator, we'll get 4. So we can say n is going to be equal to 2. So that means according to B, it's a second order reaction. Okay? So that means if we double B, which we did here, that means it's going to increase by a factor of 4, which is exactly what we saw. Okay, so then let's look at maybe 2 and 3 and see which is different. So it looks like the only thing that's changed between 2 and 3 is A. So we're going to be analyzing A here. Okay, so we'll get 0.70 divided by 0.35 to the power of n. Remember, this is like what we're trying to solve for the reaction order. Equals 6.4 times 10 to the negative 3 divided by 3.2 times 10 to the negative third. So we'll end up with 2 to the n equals 2, and we'll get that the reaction order according to A is first. So according to A, it's a first order reaction. Okay, and then last but not least, let's see, can we analyze 3 and 4? Well, no, it doesn't look like only one thing is changing, because we can see that A is changing and C is changing, so we don't want to analyze 3 and 4. What about maybe 2 and 4? Let me use a different color. Let's see here. So A is the same, B is the same, and the only thing that's changing is C. So yes, let's definitely use that. Okay, so we know that it's 0.7 divided by 0.35. So this is, sorry, I want to make this clear. This is 2 and 3 that we're comparing, and this is 2 and 4 that we're comparing. So we'll get 0.7 divided by 0.35 to the n power is the same values over each other. Okay, so then we end up with 2 to the n equals 1. We know that n equals 0, so this is, according to C, it's a 0 order reaction. Right, so that means that no matter how much concentration we change to C, it's not going to affect the rate at all. And remember, the rate is going to be the concentration over time, right? Okay, so we'll end up with an overall expression saying that the rate is going to be K times A to the power of 1, B to the power of 2, and C to the power of 0. And remember, these are all what we just determined And those are the reaction orders. So we can also write that as just rate equals k times a to the first b squared and not even include c. And we can also neglect the 1 because if we don't put the 1, we just assume it's to the first power and that it's a first order reaction. So I hope you found this video helpful. I hope it accomplished the 2 goals that I stated above of being able to distinguish between 0 first and second order reactions and being able to use this data to solve for reaction rate orders.